evaluate. And from our examples in class, didn't we use the calculator to evaluate messy stuff like that? We used the little caret button in our calculator. We reviewed how to use our calculator. So technically, it was totally fine to go to the decimal 0.544. But for future notice, if this was, say, a long answer on a test, you did not have to make it, meaning there wouldn't be like a selection of decimal answers that you were trying to figure out which one was equivalent. I would have been totally fine technically with just you guys putting 2/3 to the power of, what's 5 times 0.3? 1.5, right? So you could just set it to the power of 1.5. Is that an accurate description of the answer? Yeah. Is it simple? Yeah, as far as you can go by hand, and that's okay. That's okay. If you wanted to be super, super, super snazzy, you could have also done it like that, because it's 2/3 to the 1 and a half. And a half power is the same thing as a square root. So technically, you could have rewritten this just a little bit by, well, let's see, we would have rationalized by a root 3 over a root 3. So you could have gotten 2 root 6 all over 9. You guys can plug it in your calculator, but I'm pretty sure that decimal should check out. So we could possibly do some work, especially since it ends up being a 1.5 or a 1.5, which is a square root. We could have actually written it a little bit differently, but for the purposes of homework, they just meant, can you plug it in your calculator and work with that caret button? That's it. You already got transcendental, natural, exponential function with the natural number e. Number 14, were you guys able to pull out that it was increasing, had an asymptote, a horizontal asymptote at 1, an intercept at 0, 2. Oh, you were just matching. Letter C? Oh, because you have the older calculator, Kim? When you do a caret, it doesn't move it all the way up. Can you guys problem solve with us for just 1 second? An older calculator doesn't have that nifty ability of your guys' new operating system. It doesn't have the ability to put it in a superscript. So here's what Kim had to do. 2/3, which in the calculator, actually hers can't do the nifty fraction either. So it would have been 2 divided by 3 to the power of 5 times 0.3. Why, if she put this in, good, she put parentheses around 2/3. That answer. What's the calculator doing, or what does she need to do to make the calculator work? Adam. Yeah. Because the sad thing is, if you don't put the parentheses, this ends up equaling that, but the other way that you had it. And it used to be that I had to teach the whole class because everyone was using these. When you wrote it like this, what the calculator took it to be was 2/3 to the power of 5 times 0.3. Because the calculator does PEMDAS, so it would raise to the power first, then it would multiply. Does that make sense? So you don't want that one. You want this one, and then it should be good. Yeah. Okay, any other questions on using the calculator or on what we've covered so far? All right, number 14 was C. How did you guys make the matches? Did you think about like the shifting up and, okay, like transformations. So 14 was C, 16 was B. 24 is 7. You would have wanted to make 16 2 to the 4th power, 1-to-1 property, set them equal, solve. Number 34, were you just learning how to use your calculator or reviewing how to use your calculator? Sweet, sketch it with the graphing calculator, there it is. Horizontal asymptote ends up being at -2, shifted left 1. Anyway. Number 52, also 1-to-1 property, and not too bad a one, just 2x minus 1 equals 4, solve, 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 x equals 5/2. And I think, oh, I gave you one more, yeah. The extra credit, just to check quickly, not to cheat and write it down and pretend like you did it. The way to make the two functions match would have been to use the exponent property of addition of powers is multiplication of like bases. So you would have had to split that guy up. You could have changed 2 to the 6 to be 64. Then you could have pulled out that x and made 2 squared 4 to the x. So then you could go ahead and make that match with h. But it does not match with f. They are not the same. Okay, with that, do you guys have any other questions on the odds or clarification on the evens that you guys need? It really was that good? Robbie? 53? Okay, anything else besides 53? Going once. Going twice. Sold. All right, number 53, what's going on? Directions say one-to-one property. 2, solve. So as I look at this equation, Robbie, we're trying to solve for x, right? And the only way to solve for x is to get it by itself. Now, first of all, these e's present a problem, but only for a second because both sides are e to the power ofs. What can we do with the powers? Set them equal. Thanks, Adam. So the one-to-one property says as long as you have like bases, whether it was 2 to the, 2 to the, 3 to the, 3 to the, e to the, e to the one-to-one property says just steal those powers, they must be the same. Because of the function passing the horizontal line test, the inverse will only have one answer. Each x has one y, each y has one x. There's only one possible way for this to be true, and it's if these two are the same. But we have a quadratic. Now, if you were to look at the notes that we were supposed to be writing down in the beginning of class, for everybody's sake, wasn't there an example in the notes like this that I was able to do with the seniors yesterday? So what did I do once I had a quadratic for this example? Moved everything to one side, got one side equal to 0. Then what did I do? Factor. Then what did I do? Set each factor equal to 0. So Robbie, maybe it'll make sense why I'm about to go ahead and say we should have thought about what factors of -3 make -2. It's just 1 times negative. I end up with -3 and 1. Which are the factors, but then you still need to set each one equal to 0 to result in your final answer of -1. And double check me, guys, that look good? Does that make sense, though? Yeah. E might have made it a little bit tricky, and then the quadratic made it a little bit trickier, but otherwise, not too bad if you follow your system. And with that, cool kids, let's get back into notes and start on section 3.2. I already have a couple things filled in just for the sake of us starting this section off strong. I have a little sketch over here. I'm going to go ahead and actually make him a little bit smaller to fit in there all nice and neat. Maybe I'll move this around a little bit. Let's bring this guy down here. Okie doke. I have a big old asterisk next to the ln. Why? I don't know. Maybe he's confusing because he has an L and an N instead of an log, but he's still a logarithm. Maybe it's confusing because it's ln, but the name is natural log, not log natural. But maybe it's also because as you go higher in the sciences and the maths, ln gets used a lot. So it's really, really, really gonna be really, really, really helpful to learn and get used to ln. Reminding yourself that it is a logarithm. It's a special logarithm. It's called the natural logarithm. I already have written down for you guys, even though technically in your calculator it would just be ln of x. What that actually means is log base e. What that actually means is log base e. I also have up there for you an exponential graph of a to the x, but I also have up there a logarithmic graph to show you how they're related. Do you guys see that they're reflections across the y equals x line? Ooh, that's a thing. What types of graphs are reflections across the y equals x line, guys? Horizontal line test has something to do with this, but that's not exactly what I'm looking for. What kinds of functions? Huh? A parabola and a square root, they're reflections across the y equals x. A cubic and a cubed root, those are reflections across the y equals x. Starts with an I and ends with a versus. Inverse functions are reflections across the y equals x. inverse functions are reflections across the y equals x. Sorry guys, I realized I kind of overwrote some of my notes last year, so I'm getting them ready for today. Okay. Our goal today is basically to work with logarithms algebraically and then tomorrow to work with their graphs. So basically our goal today is to work with logarithms algebraically and tomorrow we'll finish off the section working with their graphs. So algebraically, first of all, we've talked about just on this page who is a log, who is an ln as far as a log base 10 common log and a log base e natural log. Does anybody know why log base 10 would be called a common log? Why do you think that's common? It's not really common in tons and tons of science and math examples and applications. What's so common about it? I starred this guy because he's used a lot more in higher maths and sciences. Common log, common log. Do you think the 10 is common? Why would the 10 be common? Why would we call 10 common? Maybe you need to learn a bit more about logarithms to answer this question. Be pondering that. Why is 10 common as we go through today? So far, a to the x, or we could call it b to the x and log base b. I like to put a little base b because b could be x log base a of x needs to go with, or log base b of x would need to go with the other. Reflections of each other, but we're back to graphs tomorrow. So this is just a quick introduction. They're inverses of each other, they undo each other, but only if you're like a colored pen kind of person, only when they have the same bases, okay? So only when the bases match, whatever they are, an A with an A, an E with an E, a 2 with a 2, etc., etc., etc. Only when the bases match. So real quick, what would be the inverse of this logarithm, the common log? What would be the inverse of the exponential function that could undo it? Yeah, 10, well, I like what you were thinking, Robbie. It is a 10, and it does have a power, but it's 10 to the power of x would undo. 10 to the power, that exponential would be the inverse of that logarithmic. What would be the inverse of the natural log? Hey, can you guys check out your calculators real quick and the buttons on your calculator? Just one person in a group has to have it. Everyone just peek at the calculator buttons. Can you find for me where ln shows up on your calculator? And then once you find it, tell me location. Ah! The ln is right next to the 4, kind of, upwards diagonal. Second ln is e to the x. Oh, it's his inverse. What's the button right above ln? Common log. Because if you hit it, you can go ahead and hit it. If you hit the common log, there's no base that's shown, right? So the understood base, log, is always a 10. Common log. And guys, second log, what's right above it? So if you ever forget who ln is, look at the second ln. Oh yeah, that's right, base e. If you ever forget who common log is, second log. Oh hey, that's right, his base is 10. Does that make sense? Cool. So the logarithmic functions, these two special ones, there's others, log base 2 and log base 17 and log base blah, blah, blah. But these two special ones, common log and natural log, the calculator might help you remember what the bases are if you ever forget. Okay, moving on. Let's talk about this algebraic guy. Not looking at his graph yet. Just talking about him as an equation. Not talking about his graph yet, just talking about him as an equation. Guys, remember, we got to learn the rules to play with the puzzles, just like the Sudoku. We had to learn the rules to be able to play, well, actually, and have fun with it. Or at least be able to properly do it. So there are going to be puzzles in every single homework section, but then all these foundational or basic skills are going to build up to us being able to solve something way harder at the end of chapter 3. But for right now, what do we need to learn about logarithms? Whether I call it log base b or whether I call it log base a, this little subscript down below for a logarithm is what we call the base of the logarithm. And as we already talked about, the base of the logarithm would match up with the base of the exponential function, which is its inverse. Base. X. I'm just going to call that the argument of the logarithm. Just like a square root has an argument, something underneath, just like a sine function, even though we haven't done trig yet. Even though sine has an argument, sine of x, just like a function has an argument, f of x. Logarithms have arguments too. Log base a of, if it helps, put parentheses, of x. If you need to, maybe even putting over here off to the side. Like we've been reviewing multiple times with function notation of, not times. Log times has nothing to do with math. A log only has a meaning if it has an argument inside of it. And then y is the value of the logarithm. It's the logarithmic value. Let me go ahead and put it this way. This is the first time I've ever written it this way, but that's okay. Logarithmic, I think it'll help. Logarithmic value. But there is some way of comparing a logarithmic value or relating it in a way that might help it make sense to you. Wow, some excitement going on outside. But to do that, I actually want us to do these two examples down below. And then we'll come back and try to fill in logarithmic value. If possible, it might be too late, I know. If possible, maybe you can skip like a line right here for me. If it's not too late, I'd really appreciate it if you could skip a line. Let me see if I can I separate? Oh, I can't. Okay. Hold on, I'm going to cheat the system just a little bit to give us a little more room. Nope, that's not what I want. Undo. Whoa. It's like white out, but not. Okay. Giving ourselves just a little bit more room to be able to work this out. Sorry, my OCD is just going to be a little annoyed unless it's close. It's close, right? Kiddos, I know evaluate. I know. For exponential functions, like I told Kyle at the beginning of class, evaluate was, can you plug in? It's great and all. I do want you to know. Calculator. Don't turn them on yet. Or if they are on, turn them off. Because neither of these need a calculator. We're going to use the calculator, make sure that you know how to use it, hit the buttons, etc., etc., etc. People with the older calculators, I'm sorry, yours is going to be a little harder for this one, but not impossible. But I want you guys just to think about it if it's an old-fashioned by hand problem. Guys, if we have a function and we have an x value, what do we always try to do? Plug it in, plug it in. So if I plugged in f of 32, or to find f of 32, I'm going to go ahead and change f of x with a y value real quick, and I'm going to write log base 2 of 32. Now we're going to talk more about doing it by hand. This is technically just an introduction, but any function, if you have an x value, plug it in, right? I was going to go straight to solving by hand. I want you guys to check and see if you can get it in your calculator. The final answer to this is going to equal 5. Can you guys double check I'm right by plugging into the calculator? Easy logarithms I can do some mental math on. Hard ones even I can't do mental math on. And we'll try to talk about how on earth I figured out 5 in just a second. But first of all, how do you plug in log base? If someone in your calculator, turn it so that they can see what you're trying. Just a hint, don't use ln and don't use common log directly. Don't use ln, don't use common log directly. Soon we'll see how you can use them, but you can't use them yet. Where'd you guys go? Alpha? There is a shortcut in the alpha menu, that's true. You can go alpha and then, is it window? I know, but is it the window button? There is a shortcut to getting there. You can do alpha window, and there actually is a little shortcut log just waiting for you. But the non-shortcut way? What's the non-shortcut way? Math. Isn't it under number? No. Is it under just math? Oh, yeah, it is. It is below, huh? Now, if you guys notice, that took me quite a while to get there. It's letter A underneath math menu. So I'm going to go ahead and be like, yeah, I love the shortcut. So I'm going to use my alpha window to get to log base. That is a shortcut for getting there. But the nice thing is about the newer calculators, because they had this cool subscript and superscript abilities of putting values in different places, etc. It's super nice just to plug in 2 and 32, and you guys, was I right? Okay, people with the yellow button, we're going to learn how you can use your calculator, but for right now, you have no exact equivalent to this function in your calculator. So hang in there. There is a way that you can do it, just not quite yet. I need to show you a formula first. Does anybody figure out, can anybody figure out where 5 came from? Robbie. Nice. We could actually, in calculus we call it rewriting, not quite going straight to the answer, but making something look different for our benefit. If I did 2 to the power of 5, in just a little bit we're going to review some properties either in this section or the next that actually with logarithms there's this cool thing called a power property. That if the argument of the logarithm has a power or is all raised to a power, we can actually bring that power in front. But for right now, I'm just going to use the idea of an inverse. Didn't we talk about how, on the page before, a logarithm can be undone by an exponential function of the same base? True or false? A logarithm can be undone by an exponential to the same base. Do you guys agree? How can we test this? Can you guys plug in your calculator this for me? Ready? Can you plug in common log base 10 of 100? What should it equal? Why 2? Because log base 10 of 10 to the power of 2, the log base 10 cancels out the 10 to the power of, like the square root cancels out the squared. Or like a cubed cancels out a cubed root. Or like addition of cancels out subtraction of, the exact same constant. So question, what would log base, common log, aka log base 10, of 10 to the power of 17 equal? 17. Wait. How do I see that with ln? I could do ln of second ln to the power of 3, ln of e cubed, and what should that equal? Because log base e of e to the power of 3, the e to the power of is canceled out with the log base 3. So check it. What can we do as soon as we see a log base a of a to the power of every single time since they're inverses? If we can make those bases match, we can say, sweet, the log is undone by the exponential, or the exponential is undone by the log, and we end up with the answer our calculator would give us. But this only works if we can make the bases match, right? So I want you guys to play around with letter C. Can you make the bases match? Without your calculator first. Can you make the bases match? Log base 4 of 2, but think about it. Can you make, you're in honors, come on. Can you make the bases match? P.S. Don't go changing the logarithm. That's a really bad idea. The log is the log. You're stuck with a 4. So how can I make a 2 a power of 4? Talk in your groups, real quick. Collaborate in your groups. I don't want to hear it. I know what the answer is. Talk in your groups. What do you think? How can you make 2 a power of 4? How can you make 2 a power of 4? 4 squared? No, that's way too big. 4 to the negative 1? No, that's way too small. How can I make 2 a power of 4? Nope, a power. 4 to the 1 is 4, too big. 4 to the negative 1 is 1/4, too small. What's something in between 1 and negative 1? 4 to the 0 is 1, too small. What's something between 0 and 1? Why does 1/2 work? It's the opposite of the square, or it's a square root. Better way of putting it. It's a square root because opposite is like positive, negative. You mean inverse. 1/2. It's the square root. Oh, square root of 4 is 2. Hey. Guys, can you check in your calculator that we're right? But according to our math, if we're right that 2 is 4 to the power of 1/2, or the square root of 4, this whole thing should equal 0.5 or 1/2. What's your calculator say? Log base 4 of 2. Ooh. Can anyone give me another? Oh, you need those. Thanks, guys. In your calculator, Can you guys get your calculator with a logarithm and an exponential to equal 1/2 another way? What's another way that we could get our calculator with a logarithm to equal 1/2 without using 4 and 2? 16 and 4, does that work? I'm going to use my alpha shortcut because I can't put in, oh, I don't want absolute value, lo siento. What are we doing, 16 and 4? What do you guys think, 1/2? Nice. So wait a minute, how could I use common log to get 1/2? Common log of what would equal 1/2? Ooh, this one's hard. Not 5, because 5 isn't the square root of 10. What is the square root of 10? Square root of 10.
Like 3.2.
Pause. Can't we just do this because we're smart?
Yes.
Square root of 10 is not a nice number, but I can just put in the square root of any base of a logarithm and I'll get 1/2. You guys starting to get a little bit of a feel? Now, what if I was to ask you for log base 4 of 1? What power of 4 is 1? Oh, we could do that one. Okay, it'd be 0, yeah. Wait a minute. What would be log base 16 of 1? 16 to what power is 1? Oh! What would be log base 2 of 1? What would be log base 17 of 1? What would be ln of 1? Because any base to the 0 power will equal 1. Oh, it's good to know. But if I was to do something like log base 4 of 17, 4 to what power is 17? That's when you start getting nasty decimals in your calculator, not mental math logarithms. Let's talk about this. There's this relationship between logarithms, logarithmic functions, and exponential. And we're going to totally use this relationship to our benefit. Because sometimes, maybe not this chapter, no. Definitely it will happen this chapter. Maybe not this section. But you're going to come up against equations. You'll have easy ones this section. You're going to come up against equations that have x's inside logarithms and x's inside exponential functions, and you're going to have to get them out. But there's only one way. There's two different ways of looking at it, though. What if I needed to solve for x? Let's say they gave me y as 0, or let's say they gave me y as 2, or let's say they gave me any y value and said solve for x. You get the log base away. Now, I'm not sure we're totally ready for this guy. I'm actually going to skip a couple lines and start with this guy, because we just figured out how to undo an exponential function. Did you guys realize that? How did we undo 4 to the power of, or 2 to the power of, or 10 to the power of, or e to the power of? What was always undoing that? A log. So guess what? You know how we can add to both sides? Subtract to both sides? Multiply to both sides? Divide to both sides? Guess what else we can do? We can do log base a to both sides. Yeah, it's legal. What we do to one side, do to the other. Algebra 1 at its core. We can do log base a of both sides, and guess what happens? What's going to be log base a of a to the x every single time? X. Guess what else we just did? We used a logarithm to undo, in a sense, to undo the a to the power of and just end up with x. Not even in a power, just x down alone. When we cover a property of logarithms, I can do that a bit more precisely. Right now, crossing out is actually quite illegal, but it gets the idea across. We used a logarithm to undo their inverses, to undo an exponential function and get to x, but we also changed from exponential form to logarithmic form. We also changed from exponential form to logarithmic form. Last year in Algebra 2, you might have just memorized how to go from exponential to logarithmic. Because if you just do a log to both sides, that cancels out, and so you have x. So how do we get inside an exponential? We need a logarithm on both sides. Right now, what kind of logarithm? The one with the matching base. So what do you guys think we're going to do up here if we need to undo the logarithm?
Raise it.
Yeah. But then it starts to get really weird. Because we're going to do a to the power of and then a to the power of, which I'm going to rewrite. A to the power of y and a to the power of log base a of x, and we're going to end up with a to the y is equal to, wait a minute, what happens when we raise a to the power of log base a if they're inverses? Question. What happens if you square root a square versus if you square a square root? Each other either way? Yeah. If you, they undo each other. If you square a square root, they undo each other. Now we have some like absolute going on here. But the same idea of undoing occurs whether you go one direction or the other. So whether you do log base a of a to the x or whether you do a to the power of log base a, what's going to happen either way? They cancel, yeah. Now, Robbie, I'm going to be careful. I'm not going to necessarily just do like the swoosh because technically it's kind of illegal. But the idea still occurs, meaning that's all undone and only x remains. So guess what I just did here? I went from logarithmic form to exponential form. Could you memorize every time that you're given a y equals log base a of x, it becomes an a to the y equals x? Yes. Could you even memorize the base of one is the base of the other? So it's base to the, I say back forth, base to the go across, base to the power equals the argument, base to the power equals the argument, a to the y equals x. You could memorize it and go from one to the other. Or you could understand the math and say, oh, whatever, a to the power of both sides, whoosh, 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 done. One is a mathematical way of getting there, and one is a memorizing way. Algebra 2, you probably memorized. Pre-calc, maybe you'll understand why. It is what it is. But before we totally go into just playing around with these guys algebraically, we need to talk about one more thing, and that's called the change of base formula. It's called the change of base formula. It's actually super, super practical in so many ways. It makes some calculus, what we call derivative rules, possible that would have been impossible otherwise. Just one little application. It allows you to take a problem of different base. So it is helpful. It's just one of those for right now, memorizing kind of things that we need to do. It's one of those memorizing things we need to do. Change of base formula. If I have a logarithm of a base that I want to change it, for my people with the yellow button calculators, you don't like log base anything besides 10 or e. You don't like anything besides the common log or the natural log because you don't have the spiffy extra functions of the newer calculators. You have to use this formula because this formula says, give me a logarithm of any base, and I can make it the base that you want, a different base b, as long as you follow this pattern of dividing the new log of the argument over the for people with the yellow button calculators, or for any of us that might come up against common logs or natural logs and start liking them more than the other bases, we can make any logarithm into a common log just by division, or we can make a natural log just by division. So an application of this guy, if I can, here's the big property. If I can, which I can, this is called the change of base formula. Any logarithm, or I should say a logarithm of any base to be another base, we can change it to common log, we can change it to natural log. So for instance, if you were needing to solve this example, and let's say you had one of the yellow button calculators, f of 32 is equal to log base 2 of 32. You have no cool little feature of log base, whether with a shortcut or in the math menu. It's not there. You could just say, oh, hey, it's common log of 32 all over common log of 2. You have those buttons. Or you can make it natural log of 32 all over. Natural log, you're back. 2. And so even though you don't have that cool log-based feature, you're going to use this formula that everybody has to memorize anyway. Don't worry, I'll force it as far as how the test is going to ask the questions that they're going to have to know. And when you put this in your calculator, you will end up with the exact same answer that we got of 5. Dun, 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 dun. If you don't like the log of the base or the base of the log, you can change it, but you have to do it legally with the change of base formula. You guys have it? So, what are we going to do when they come for you? If you have an example like this, and we have to solve for x, pause, hold on, a few more rules. Just a few more properties, I should say. I'm going to star the ones that I think, or I'm going to highlight, let's do that. I'm going to highlight the ones that I think are the most helpful, even super important too. We've already talked about actually both of these in some way, shape, or form. The bottom two are going to be the most helpful, as in we're going to use them over and over and over again. The one-to-one property and the inverse property. The inverse property you guys just saw me do. Log base a of a to the x will cancel out to just be x. And a to the power of log base a of x will, maybe I should say reduce, will be undone to x. Ooh, undone, even better. Remember the undoing? So the inverse property says they undo each other to x, and they undo each other to x, whichever way you go. The one-to-one property says make the bases match, and the arguments must be the same. Number 2 is just letting us know whenever you have a log base a of a, it's like log base a of a to the 1. So everything is undone but the 1. Everything's undone but the power. And then the first one says any logarithm that you take of 1, like we talked about, log base 2 of 1, log base 17 of 1, log base e of 1, log, in order to equal 1, the power will always be 0. So we could always rewrite it as base to the 0. And as soon as you put in base to the 0, everything's undone but the 0. So I'm going to go and highlight those ones as well, but just the important parts. This is a fact, and this is a fact. That's just the reason why. So guys, how are you going to go ahead and simplify or solve or get to x on the first example that you see right there? There are 2 ways to get there. What's one way to get to x? What do I do with the log? The 5x plus 3 is trapped. The 12 is trapped. 2 ways. One way is to ask what's the base, and the base is, you can do 10 to both sides. Is that going to be helpful for both sides? Yeah, so 10 to the power of this side and 10 to the power of that side. I do the little powers because otherwise you're not exactly, I don't know, it gets confusing sometimes. But 10 to the power of both sides, we end up with 5x plus 3 is equal to 12. Wait, last night's homework. Wasn't there this cool one-to-one property that says as long as the bases match? What's true about my logarithms? They match, and there's no extra like plus or minus outside the logarithm. So as long as you have 2 logs, oh, it's right here. As long as you have 2 logs, the same bases with 2 arguments, those arguments must be the same. Then couldn't we, with some quick math, subtract 3 both sides, divide by 5, and end up with, what'd you guys get, 9/5? Got it. Oh, that's just one-to-one property, but you could also do 10 to the power of both sides, and technically you're right. You're just doing the math behind the property. So what if you have something like, ooh, hoo-hoo, this guy. All right, let's have some fun. Let's have some fun. One-to-one property. No, there's not a logarithm on both sides. That's all right. Could you memorize going from logarithmic form to exponential form and then trying to make this match? I suppose. But what's an easier way to get rid of log base 3? What undoes a log? Second log, what undoes a log? To the power of, right? An exponential. So which exponential do I need? E to the? No. 10 to the? No. 3 to the. So I'm going to do 3 to both sides. 3 to the left, 3 to the right. What happens to 3 to the log base 3? Everything's gone but 2x. Everything's undone. X. And what's 3 to the 4th? Oh, you guys are spiffy and can say that's 81, right? 3 squared, 9. 3 squared, 9. 9 squared, 81. What's x? 81 over 2. Well, that's not bad. Ooh. What about number 2? Their bases don't match. Do they? Maybe we have to just solve this guy without even thinking about that guy? Because we can't like do 9 to both sides. That doesn't work. We can't do 3 to both sides. That doesn't work. We can't use 1 to 1. They don't match. So let's think about this guy. What power of 9 is 27? Well, 27 is 3 cubed, right? Wait. Or couldn't we say that 27 is 9 to the 1.5? Can we say that? Isn't it 9 and then a half of 9? A half power of 9? Pause. So couldn't we make this log base 9 of 9 to the power of 1.5? There's 1 whole 9 and 1 square root of 9. So what's this side equal? That was rough. Now what can I do to solve? How do I get rid of logarithms? 3 to the power of 3 to the power of, and we end up with, you guys can get out of here as soon as you write 3 to the power of 3 halves. Dun, 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 dun. That was rough. Other way of writing it, I had to end on a fun one just to get you guys, I don't know, your brain juice flowing. Because homework isn't due until after retreat, but you can do almost anything besides graphs, and maybe some of you can even do those tonight. Laters. Laters. P.S. Precal has a test tomorrow in Chapter 2. Some of you might want to get some tutoring hours in. You could help. Bye.